Okay, so let's dive into some pretty big ideas about the universe, how it began, how it might end, and the role of information in all of this.
Hmm.
You've been sharing excerpts and notes, even some analogies that have me really thinking.
Yeah,
So today we're going to try to connect the dots, see if we can get some deeper insights.
sounds good.
You've even proposed this idea of a cyclical universe,
Right.
where complexity eventually collapses back into order, setting the stage for another Big Bang.
Exactly, and it's like the universe keeps hitting that reset button, but in a way that preserves some kind of fundamental blueprint. I really liked your comparison to phase locking.
Yeah, like how those flashing turn signals on cars sometimes sync up, even if they start at different times.
Hmm.
Could the universe, with all its diverse forms of energy and matter, eventually lock into a simpler state through a similar process?
That's a great question, and it really highlights how patterns we see in everyday life, they might actually hold clues to the workings of the universe.
Mm.
Think about phase transitions like water changing from liquid to ice, or even the Big Bang itself, which is a transition from an incredibly hot, dense state to a more structured one as the universe cooled.
Right.
So could there be a similar principle at play, but on a cosmic scale, where forces we don't yet fully understand drive the universe from complexity to order?
That makes me wonder, though, wouldn't a transition like that require some kind of mechanism?
Yeah,
Like a force that simplifies all that complexity back into a more ordered state?
exactly. That's one of the big challenges in exploring these cyclical models. We need a plausible explanation for how such a reset could happen.
Mm-hmm.
Some theories suggest that gravitational collapse could be the key. Imagine the universe reaching a point where gravity becomes so dominant that it pulls everything back together,
Oh, wow.
creating a kind of cosmic implosion.
So everything collapses, but then what?
Right.
How does that lead to a new Big Bang and a new cycle?
Well, there are some intriguing ideas about that as well. One concept is this idea of holographic encoding at the boundary of the universe.
Okay.
This is where your analogy of a cosmic hard drive storing information for the next cycle becomes really relevant.
Uh-huh.
The holographic principle suggests that information within a region of space can actually be encoded on its boundary, like a two-dimensional surface surrounding a three-dimensional space.
So even as the universe collapses, information about its structure and maybe even its history could be preserved on this cosmic boundary.
That's the idea, and it's particularly fascinating when we consider the event horizon of black holes.
Right.
These regions of spacetime are so dense that nothing, not even light, can escape them once it crosses the event horizon.
Wow.
Some physicists believe that the event horizon might act like a holographic surface, encoding information about everything that falls into the black hole.
So black holes, which we often think of as these destructive forces, could actually be key players in preserving information across cosmic cycles.
It's a possibility that researchers are actively exploring. And this ties into one of the central questions you raised. How could quantum information be preserved across these cycles? If information is truly fundamental as you propose, then it shouldn't simply vanish, even in the face of a cosmic reset.
It really challenges our whole idea of what's truly fundamental.
It does.
We tend to think of energy and matter as the building blocks of reality.
Yeah,
But what if information is even more basic than that?
right.
What if it's the blueprint that guides how energy and matter behave?
That's a powerful shift in perspective, and it's one that physicists are taking increasingly seriously. It links back to that famous equation, aim-sequel, which shows this deep connection between energy and mass.
Yeah.
But maybe there's an even deeper level to explore here. What if information is the key to understanding how energy and mass are organized and expressed?
So instead of viewing the universe as simply stuff, maybe it's more like a vast network of information constantly evolving and transforming.
Precisely. And if that's the case, then the Big Bang might not be the absolute beginning of everything. It could be a transition point in a much grander cycle, a point where information is reshuffled and rearranged, but not destroyed.
That really challenges the traditional view of the Big Bang.
It does.
If information is never truly created or destroyed, then the idea of a single starting point where everything suddenly pops into existence might not hold up.
Right. It opens the door to alternative cosmological models that challenge the notion of a singular beginning.
Okay.
Some models propose a universe that's eternal, constantly expanding and contracting, while others envision a universe that's constantly unfolding without a defined starting or ending point.
These are pretty radical departures from the standard model of cosmology.
They are.
What kind of evidence is there to support these alternative views?
Well, there are some tantalizing hints. For instance, there are anomalies in the cosmic microwave background radiation, the faint afterglow of the Big Bang.
Yeah.
That might point to processes beyond the standard model.
Mm.
There's also the issue of the low initial entropy of the early universe, which is difficult to explain if the Big Bang was truly the absolute beginning.
So we're still piecing together the puzzle.
We are.
But it seems like there's a growing body of evidence that suggests the universe might be far more complex and interconnected than we previously thought.
Absolutely. And one of the most exciting aspects of this exploration is the potential for information to be encoded not just in matter and energy,
Right.
but in the very fabric of space-time itself.
That's a pretty mind-boggling concept.
It is.
How could space-time, which we usually think of as a background for events, actually store information?
This is where we get into the realm of quantum gravity, the attempt to unify Einstein's theory of general relativity with quantum mechanics.
Okay.
Some theories propose that space-time isn't smooth and continuous at the smallest scales,
Yeah.
but rather has a quantum structure, a kind of graininess that can be described using the principles of quantum information theory.
So we're talking about a universe where information isn't just like contained within matter and energy, but is actually like woven into the very structure of space-time itself.
It is a really profound concept, and it really has implications for, how we understand the potential for information to survive across these cosmic cycles we were discussing.
Right.
If space-time has this quantum structure, then perhaps the information it encodes could endure even the most dramatic transformations of the universe.
So it's like the universe has a built-in backup system for information.
Yeah, that's a great way to put it. And there are a number of researchers exploring specific mechanisms for how this might work. For example, one study focused on a theoretical model of information preservation in a very specific type of spacetime called Kerr-Newman spacetime.
Kerr-Newman spacetime.
Yeah.
That sounds pretty complex.
It is?
Is there a way you can help me visualize what that is?
Sure. Imagine a rotating black hole with an electric charge.
Okay.
That's essentially what a Kerr-Newman black hole is.
Okay.
Now, the spacetime around such a black hole exhibits some really unique properties, including the possibility of these theoretical loops in spacetime called closed time-like curves, or CTCs.
CTCs aren't those the things that might make time travel possible?
Exactly. There are these hypothetical pathways through spacetime that could potentially allow for time travel. Now, while that sounds like science fiction, the mathematics of general relativity actually suggests they might be possible, at least in extreme environments like those we find near rotating black holes.
Okay, so how do these CTCs relate to the study on quantum information in these cyclical universes?
Well, this study, while still very theoretical, explores how particles entering these CTCs might behave in terms of the quantum information they carry. The researchers applied a principle called Gavesino's restoration principle, which suggests that information seemingly lost during a process might actually be restored under certain conditions. It's like information playing a cosmic game of hide-and-seek.
So information might appear to disappear, but it could be encoded or hidden in ways we don't yet understand.
That's right, and this research proposes that these CTCs might be one of those hiding places. It's a really intriguing avenue for further investigation.
Definitely. So we've got one study that suggests information might be preserved in these theoretical loops in space-time.
Right.
What about the other studies you mentioned? What other potential mechanisms are they exploring?
Another prominent model that addresses quantum information in cyclic universes is Roger Penrose's conformal cyclic cosmology, or CCC. You might have heard of it.
CCC, yes. Doesn't it propose that the universe goes through these incredibly long cycles called eons?
Exactly. CCC suggests that our universe isn't the first, nor will it be the last. Instead, it's part of an endless cycle of expansion and contraction, with each cycle potentially leaving an imprint on the next.
That's such a vast concept, but how does quantum information fit into this model? How could information survive across these incredibly long cycles?
Researchers are proposing a unitary version of CCC, meaning the evolution of the universe is governed by quantum laws that inherently preserve information. According to this model, information isn't lost as one aeon transitions to the next. Instead, it gets carried across these cosmic epochs.
So each cycle inherits information from the previous one, almost like a relay race, but on a cosmic scale.
That's a great analogy. And what's particularly interesting is the role of entanglement. The model suggests that entanglement with specific quantum gravitational degrees of freedom might be the mechanism by which information gets carried across these vast stretches of time.
Okay, entanglement and quantum gravity, we're definitely getting into some deep physics territory here.
We are, but that's where things get really exciting. It's often at the intersection of seemingly disparate fields that the most groundbreaking discoveries are made.
I totally agree. So we've got CCC offering a way for information to be preserved across these grand cosmic cycles. What about that third study you mentioned?
Right.
What approach does it take?
The third study looks at the quantum structure of spacetime itself. It proposes that spacetime isn't just this smooth background as we often think of it, but rather has a quantum structure that might be described using the principles of quantum information theory.
Wait, so you're saying space-time itself might be made of information?
That's what this study is proposing. It suggests the fundamental building blocks of spacetime itself could be linked to quantum states, and more specifically to two qubit states of these hypothetical massless particles called gravitons.
Hold on, gravitons, those are the particles that are thought to carry the force of gravity, right? But we haven't even directly detected them yet, have we?
Not yet, but they are a key prediction of many theories of quantum gravity. And this study proposes that they not only mediate gravity, but they might also form the very fabric of spacetime.
So we're talking about a universe where information is not just a property of matter and energy, but is actually woven into the very essence of space and time. And gravity plays a much more fundamental role in all of this than we ever imagined.
That's the core idea, and what's really exciting is that this model offers a potential mechanism for quantum information to persist across those cosmic cycles. If spacetime itself has a quantum structure, then perhaps the information encoded within that structure could survive even the most extreme transformations the universe undergoes.
Wow, that's a mind-boggling concept. It's almost like the universe is this massive quantum computer constantly processing and storing information within its very essence.
I love that analogy. It really captures the potential depth and interconnectedness that these models suggest.
So we have these three studies, each offering a different perspective on how quantum information might be preserved across cycles in these cyclical universe models. Where do we go from here? What are the next steps in exploring these ideas further?
Well, these studies are incredibly insightful, but they're just the beginning. They give us a framework for thinking about these complex concepts, but there's still a lot of work to do.
What are some of the biggest challenges we face in trying to understand this phenomenon of information potentially surviving across cosmic cycles?
One of the biggest hurdles is empirical verification. These are highly theoretical concepts, and it's really difficult to design experiments that could definitively prove or disprove them.
Right, we're dealing with phenomena that happen on cosmic scales over vast stretches of time. It's not like we can just create those conditions in a lab.
Exactly, so we have to get creative in searching for evidence. We might find subtle signatures in the cosmic microwave background radiation, or perhaps the gravitational wave background might hold clues. It's really like solving a detective story, but on a cosmic scale.
That sounds like quite the challenge. What are some of the other hurdles you mentioned?
Another challenge is developing a greater level of mathematical rigor. These models are still largely conceptual. We need more robust mathematical frameworks to fully grasp the dynamics of information preservation across these cosmic cycles.
So we need to translate these intriguing ideas into the language of mathematics to test their validity.
Precisely. We need equations, theorems, proofs, all of that to rigorously describe how information is encoded, preserved, and potentially retrieved across these vast cosmic transitions.
It's like trying to write the instruction manual for the universe's information storage system. No small feat.
You're absolutely right. But it's an essential task if we want to understand the true nature of reality. And the third challenge I mentioned is the need to integrate these models with existing physics.
What do you mean by that?
These models of cyclical universes and information preservation can't just exist in isolation. They need to fit within the broader framework of established physics, things like quantum mechanics, general relativity, and cosmology.
So it's like trying to fit a new piece into a giant jigsaw puzzle. It has to connect seamlessly with everything we already know about the universe.
Exactly. These models need to be consistent with the laws of physics as we understand them, and they need to be able to explain the observations we make about the universe around us.
Okay, so it sounds like there's a lot of work ahead, but it also sounds like an incredible journey of discovery.
It really is. We're pushing the boundaries of human understanding, exploring the most profound questions about the universe, its origins, its potential end, and the very nature of reality itself. And who knows what amazing insights await us as we continue to explore these mysteries.
That brings us back to your deep dive into these concepts. You mentioned this idea that information might be even more fundamental than energy, which is a pretty bold statement. Can you elaborate on that a little more? It is a bold idea that information might be even more fundamental than energy. I'm really curious to hear more about how you arrived at that.
Well, it starts with thinking about what we actually mean by those terms. Energy is the capacity to do work, to create change, right? But what is it that guides how that change happens? What shapes how energy is organized and expressed?
That's where information comes in. It acts as the blueprint, the code that determines how energy manifests in the universe.
Exactly. Information provides the structure, the pattern, the order. It's the difference between random noise and a beautiful symphony, both of which involve energy but are fundamentally different in how that energy is arranged.
And you're suggesting that information isn't just a byproduct of energy, but something deeper, something more fundamental.
Yeah, I'm proposing that information could be the underlying essence of reality itself, and energy is just one way that information expresses itself.
Wow, that's a pretty big shifting perspective. It's like saying that the universe isn't just made of stuff, but of bits, like a giant cosmic computer program.
That's a great analogy, and it aligns with some of the most cutting-edge ideas in physics today, where information is increasingly seen as playing a central role in quantum mechanics, cosmology, and even the nature of space-time itself.
Let's bring this back to your initial idea about a cyclical universe where complexity eventually gives way to order, which then sets the stage for a new cycle of complexity. Does this new perspective on information change how you view those cycles?
It definitely adds another layer. If information is fundamental, then these cycles might not just be about physical transformations of matter and energy, but about the evolution and processing of information itself.
So each cycle of the universe is like a learning process, a way of exploring new possibilities and expanding the cosmic storehouse of information.
That's a beautiful way to put it. It raises all sorts of fascinating questions. For example, if information is preserved across cycles, could there be echoes of previous universes embedded within our own? Could we somehow tap into that ancient knowledge?
That's a mind-blowing thought. Like the universe has a memory that we might be able to access if we just knew how.
Exactly. And that's part of what makes this exploration so compelling. We're not just probing the physical universe, but the vast realm of information that underpins it, a realm that might hold the keys to understanding the deepest mysteries of existence.
It sounds like you've only just begun to scratch the surface of this idea. What are your next steps in this exploration?
Well, for me, it's about diving deeper, reading more, learning more, connecting with others who are grappling with these same questions. And it's about searching for those subtle hints, those faint echoes of information that might be hidden within the fabric of our universe.
It sounds like an amazing journey.
It truly is. And the most exciting part is that it's a journey anyone can join. All it takes is a curious mind and a willingness to explore the unknown.
Well said. And on that note, we've reached the end of our deep dive today. But as you said, this is really just the beginning.
Absolutely. It's the beginning of a journey that could lead us to a profound understanding of the universe and our place within it.
So to our listener out there, keep questioning, keep exploring, and keep pushing the boundaries of what we think we know. Who knows what incredible discoveries await us just around the corner?
After all, the universe is full of surprises, and the pursuit of knowledge is the greatest adventure of all.